I want a wireless one. Okay. I'm attached. You know, it's hard to walk around when you got a wire attached to you. All right, so we're going to talk about conics. And today there are 4 kinds of conics. And we're first going to learn how can you identify the equation that you have to know what kind of conic it is. So because I can only have up one of them at a time, you have a packet that shows all 4. There are 2 on the front and there are 2 on the back of that first sheet. So what I'd like you to do for just a moment is I'd like you to look at the standard form versus general form of parabola, okay? Then look at circle and maybe flip over to ellipse and hyperbola on the back and see if you can determine what's different about the parabola equations, very different from those versus the other 3. Because that's one of the things, if we can identify something that's different, then maybe that'll make it easier to know it's a parabola. So what do you think? You're looking at your parabola formula, and then you're looking at your circle formula, and you've got to think about standard and general. You can't just look at standard, for example, because some people would say, oh, it has circles, has parentheses in it, and there's 2 of them. And this one doesn't have but 1 set of parentheses sometimes in it, sometimes 2. So what do you notice? She said adding on that. Okay, let's go with that thought. What about ellipse? Is it adding? Or what about hyperbola? Okay, there's subtraction. Okay. Is it subtraction even no matter whether x or y is first? There's even subtraction, some of this down here. So that might give away hyperbola, because ellipse has plus between them, doesn't it? Now, it's not plus between everything. Okay, they've got fractions in some of these. Anybody see something different about parabola that you don't see in the other 3? All right, there we go. That's a dead giveaway. This only has 1 square in the formula. Does everybody see that? Yeah. All right, so the thing you want to write on your packet here is only 1 squared term. And it doesn't matter if it's in general form or if it's in standard form. It only has 1 square. Now, in the standard form, you've got a parenthesis with a square on it, where in general form, the first term is squared. And you only see 1 in every one of those. Does everybody see that? Now, that would give that formula away, so that if I'm working with a mixed up list of formulas and I see 1 square, I know I've got parabola. All right, so parabolas have 1 square. Let's talk about circles then. So we look at circles, they have 2 squares here, they have 2 squares over here. All right. And then when we look at ellipse, we have 2 squares here, 2 squares there, 2 squares down here, even in general form at the beginning. And in a hyperbola, they all have 2 squares. So squared's not going to help me, is it? But what did y'all notice about hyperbola that was different? The subtraction. Okay? This subtraction sign here between the fractions or between the squares, and you only look at squares in these problems to know something about them. So because of that, because you only look at squares, that focuses you clearly into subtraction. Definitely gives away hyperbola. The squared terms are subtracted. So that's very, very important. If you see 2 squared terms, whether they're in parentheses or whether it's already been all multiplied out and you see them at the beginning, it's got to have subtraction to be hyperbola. Now, other than that, we've got to find something really different about our ellipse versus our circle. Let's talk about what an ellipse is and what a circle is. Well, wrong way. Okay, now ellipse is an oval. Oval's like layman's terms. That's not a math term. Ellipse is a math term. And you'll notice they can be turned different ways. They can be longer up and down, or they can be longer across. And how far it is from the center is really important because that's what gives it that elliptical shape. So that's kind of going to be obvious from some of these numbers if you look at them, because wouldn't you think the y would be longer in this problem? And wouldn't you think the x would be longer in this one? So what if it's the same both ways? It's a circle, which is why the circle formula doesn't have any numbers underneath it. If I divided this 25 over to the other side and put it like the others were always equal to 1. Hyperbolas and ellipse patterns in standard form are always equal to 1. If I divided this problem out so that this would be 1 over here, then these would be the same. And that means it would have the same distance from it all directions. So a circle's just a special ellipse. Kind of like a square is a special rectangle. Not every circle's not every ellipse is a circle, but every circle is an ellipse. Okay? And so because of that, they don't like to put the two 25s under here. They just like to put it over here and have it all on one side since they're the same number. So when you're looking at it, you have to think about, okay, I would divide this and these two would be the same versus them being different numbers. If they're different numbers, it's ellipse. If they're the same number on your squares, then it's a circle. So when you look over here, don't they have the same coefficients? But when you look at ellipse and you look at the general form, do they have the same? And in this particular case, you have to be very, very careful because which one looks bigger here may not end up being which one is bigger when you try to put it back into this format, but at least I can see they're not the same, correct? So that gives it away. If they're not the same with addition, it's an ellipse, and if they are the same, it's a circle. And it has to have addition. That's really important because we just noticed that hyperbolas all have subtraction. Does everybody see that? Okay, so let's write something on circle. So to be a circle, it has to have the same coefficients on the squared terms. That are added. So when my general form said x squared plus y squared, or if it said 4x squared plus 4y squared, that would mean they're the same. Or if they're underneath both of these, they've got to be the same. And if there's nothing underneath it, then they're definitely the same because they both be 1, right? So they got to have the same coefficients or the same number underneath the problem on their squared terms, and they have to be added. And so the only difference between this and ellipse, I'm going to copy this. Okay, what word am I going to change for ellipse? Yeah, change the word same to different. Exactly. They have different coefficients, or the number underneath the fraction is a coefficient, by the way. It's like anything outside of a parentheses is a coefficient in this problem. So whether it's the numbers underneath or it's the numbers in front of your squared terms, it's the same concept. And so we're writing different coefficients on the squared terms, but they have to be added. So subtraction's hyperbola, so we only have that big difference between the adding of ellipse and circle. We know parabolas have one square, hyperbolas have two squares and are subtracted. These have two squares that are added, but they have different or same coefficients. So the key is you've got to be able to identify which conic you're working with. If you don't know which conic you're working with, it won't help you to determine what to do with it, because you find different information with each kind. And so, for example, As you can see in some of these graphs, this parabola opens up like we normal. Well, we're now going to look at parabolas that open left and right. That definitely is not a function. It would not pass the vertical line test. I can't solve this problem for y and work it in my calculator. I have to know how to do them by hand because they're not functions. And that's really important. So we need to know how to work with these formulas, and we wouldn't know what to do. I mean, we know that they have a vertex, okay, for example, with parabola. We know circles have a center and a radius. At least I hope we learned that back in Math 3. And, well, ellipse kind of has a center, but it has two different measurements. It has a different measurement going across than up and down. So that's like having, it's not radius, but it's two different measurements, so we'd have to know. And then hyperbolas, it looks like we got two parabolas going on here. So we're going to have to know what is it we have to have in order to work with each of those questions. And it's not the same information on each one. And because of that, we have to know what formula we have so we'll know what to pull out of it. So on the next page in your packet, you have something that looks like this. Huh? Okay. All right, so you have 10 questions. It's a mixture of formulas, and all you're doing here is you're identifying each conic. You're going to tell me, is it a parabola, a circle, a hyperbola, or an ellipse? And then, if you figured out what in the formula told you that, I want you to go in and maybe just make a little jotted note down there, like 1 square, for example, if that's what gave it away. Because I want you to be able to identify it. So go through this packet very quickly, look around for, and you know, I do this in an organized method. I go look for all the parabolas first, because if you can find all the ones that have the 1 square first, doesn't that rule a lot out? So try that. Alright, so next thing we're going to do is learn how to fill in a perfect trinomial. A perfect trinomial is that problem where we square the first, we square the last, and we double the middle. So we're trying to figure out what did they square to put here, but what would double to make the middle. And so that's why you want to learn this formula. ax squared plus bx plus c. Because to find c, you have to do b divided by 2 quantity squared. And that will give you the number that goes on the end of your c. So for example, on this one, we would take 18 divided by 2. That makes 9. So squaring 9 would give me that perfect square trinomial of 81. It's because I can think about what would I square to get 81? What would I square to get x? That would be x and 9. And doubling that makes 18x. So if I do 20 divided by 2, quantity squared, I get 10 squared, which is 100. But not everything works that nice. Here I have a negative 1. I don't know how to divide negative 1 by 2. So I just square each one individually. 1 squares 1, 2 squares 4, and negative times negative makes a positive. So you just do the top and bottom individually. So if you do that for number 4, it doesn't divide. So you'll get 9 and 4, because 3 times 3 is 9, and 2 times 2 is 4. And squared negatives make it positive. So on number 5, if you take and divide by 2, you'll get 12 squared. And the negative doesn't matter because it's negative times negative makes a positive. So 12 times 12 is 144. I don't pay any attention to the negative. You'll notice every one of these problems had a plus at the end of it because it can't be negative. If you take a negative times negative, you always get a positive. So you're just trying to fill in the blank to make it into a perfect trinomial. Alright, so I'm looking at number 4 because that's a fraction. So we got to know how to do this with all kinds of numbers. It's not just for whole numbers, although some of our whole numbers or integers don't divide evenly by 2. Clearly 2/3 is not going to divide evenly by 2, but we need to discuss how to do that because sometimes we forget how to do some of this math. So if we take 2/3 and divide it by 2, And then we'll think about squaring it after that. How you divide fractions? Flip and multiply, okay? So we'll take 2/3 times 1/2, because I'll have to stick a 1 under that 2 so I can flip it. And what did we learn back in our last unit that helps us so clearly to multiply that together quickly? Cancel the 2's, right? And now I have negative 1/3 over 2. Now I could have multiplied the tops and the bottoms together and reduced, but it was quicker to see those 2's cancel, and that saves me not having to multiply that. So now if I square each one individually like you were doing earlier when they didn't divide out evenly, I get what? 1/9. And that's how number 8 is also worked. So if you want to take a few more minutes to try a few more of those. So if I go back to the beginning of this whole lesson, sure would be nice if I had some parentheses were squared, because I can pull numbers out of that and know where to plot them. But when it's in this format, see how I don't know what to pull out because I don't see a parentheses to pull the number out of? For example, I know for sure that this is going to touch negative 2 because that's the zero of the function right there. And I know this one's going to touch 3. Because if I set that equal to 0, it'd be 3, wouldn't it? I can't see that in general form. That's why we're going to have to learn completeness square. We're going to have to learn how to take this formula in general form and turn it back to a standard form. And as you can see, each conic, the format's slightly different. And when they put them in general form, they tend to want to put all the squares and then all the linears and then the constant on the end. Well, that's because they've multiplied out. They've squared the first, squared the last, doubled the middle of that, squared the first, squared the last, doubled the middle of that, and added all the terms together and put them in order. Not real user-friendly that way. So this process that we're going through is going to allow us to take a trinomial that has been multiplied out and turn it back into a binomial squared. So here's your two formats of what you can see. We know that we've got ax plus squared plus bx plus c format, and that we're wanting to change it into two terms squared individually. Before they were squared, what were they? Sometimes it'll have a plus and sometimes it'll have a minus. And what you'll notice is that comes from the middle. Can't get that off the end because the end's always positive, right? So when I look at this, I know immediately this is going to have a subtraction sign. So we're going to factor this. These are perfect squares. No reason to do the grouping method. That's the long way. But if you want to do grouping, you could go right ahead. But these are perfect. And perfect you can do in 2 seconds. It's so simple to do perfect. And because all of these have a 1x squared, it's even quicker. You just square root them, and there you go. Because if I double that now, will it make the middle? Yeah. If I do 2 times x times negative 8, I get the middle. And that's my check. To make sure I've done it right, I could do that in my head every time to make sure that I've got the right items in the parentheses. Because if your parentheses are wrong, your whole entire problem will be wrong. Because you'll go off plotting things in the wrong place. So this makes my x minus 8 quantity squared my answer to the question. I don't need to have an equal mark there. I need it over here. So that's how you factor perfect squares. Now, you could multiply the first number times the last number and make the list, but it'll take twice as long. This is quick factoring. And even if there's a number in front of x squared, it works just as easy. For example, what would the first term be for 4x squared? 2x. What would 9 be? And am I going to put a plus or a minus? Plus, because the middle is plus. That's all you do. So what am I going to have for the next one? Let's square root the first and the last. 4x what? Why? It's negative in the middle. You got to have minus. So that's the only piece you have to really pay attention to the middle for. The middle doesn't do much for you except check it. For example, 2x times 3 is 6, and if I double it, it makes 12x. 4 times negative 1 is negative 4x, and doubled is negative 8x. That's all the middle does for you, is the check. It's just the check to make sure you've done the math right. So on our next one, what's the square root of 169? Does 13 double make 26? All right. But it gets a little harder when you go into the ones that they have the fractions sometimes in the checking part. Not hard to take the square root of, just the checking part. Because if you get x, and what is 49 over 4 square root to be? 7 over 2, okay? And I'm going to put a plus because it's positive and have my quantity squared. So if I double this, that means I'm multiplying by 2. Doesn't that cancel the 2 out on the bottom and leave me with the 7 I'm supposed to have in the middle? Okay. And if I do the next one, and I say the square root of x squared is x, what's the square root of 25 over 4? 5 over 2. And if I double that, that gets rid of the 2 again. But how's it going to make it negative 5x? That's right, we're going to put a subtraction sign in there for the negative. How? This is 2 steps, okay? I've shown them to you individually by showing you that first we have to know how to get the right number on the end, because if the number on the end is square rootable, then we can do this process to it. All right, so try a few of these on your own.